So today I will explain the basics of OpAmps in a very simple way, and also the difference between an OpAmp and a comparator. Because in the next video I'm going to test some OpAmps for my battery analyzer, and without knowing the basics, some of you would have no idea what the hell I'm talking about. And of course, yes, I ordered some OpAmps from eBay, and I was going to make a video about what OpAmps to use in my battery analyzer, but instead of it, I'm going to make a video about what not to use in my battery analyzer, because I probably ended up ordering some fake ones. In the next video I'm going to test these fakes, and show how to test them and figure out what they actually are. But before this, you need to know some basics. So let's take a look at OpAmps and also comparators. Both OpAmps and comparators have the same symbol, and they are very similar. They have two inputs, one output, and two supply pins. The supply pins are the positive and negative, or in some cases positive and zero. There are two inputs, an inverting input with a minus symbol, and a non-inverting input with a plus symbol. Now let's talk about the difference between a comparator and an OpAmp. A comparator, as the name suggests, is to compare two voltages. It compares the voltages on the two inputs, and if the voltage on the non-inverting input is higher, then the output is high. The voltage on it is close to the positive supply rail, basically. There is basically some internal transistor switching it to the positive rail. And if the inverting input has a higher voltage on it than the non-inverting, then the output voltage is low. And then the other internal transistor is on and pulls the output low, close to the negative supply rail. A comparator typically compares two voltages at the inputs and has no feedback from the output to the inputs. And its output is either high or low. It's not working in the linear region. Comparators can be used for an overvoltage or undervoltage protection, to indicate a low battery voltage, to stop charging a battery when it's full. OpAmps are very similar, but when using an OpAmp there is typically a feedback from the output back to the inputs, and this feedback is constantly trying to get the inputs both to the same voltage. And the output of an OpAmp is working in the linear region. It's not a logic output. It's not high or low, it's anywhere in between. A very simple example of a circuit with an OpAmp, a non-inverting amplifier. This amplifies the input signal without inverting it, and the amplification ratio is set by these feedback resistors. In this case, this resistive divider divides by 3, so the output voltage is going to be 3 times the input voltage. Let's, for example, put 2 volts to the input, and let's say the output starts at 0, so this resistive divider also produces 0 at the inverting input, and the non-inverting input has a higher voltage on it, so the output will travel up. The voltage on it will be getting higher and higher until it reaches equilibrium. The voltage at the output basically rises until it reaches 6 volts. And at this point, the 6 volts at the output divided by 3 by this resistive divider produces 2 volts at this input. Now both inputs are 2 volts, which means it reached equilibrium. And the output voltage no longer goes up, it stops at 6 volts. And now let's try to have minus 1 volt at the input. This resistive divider still produces 2 volts by dividing 6 volts by 3. And so the voltage at the inverting input is higher. So the voltage at the output will travel down until it reaches equilibrium. It will basically travel down all the way to minus 3 volts. And at this level, this resistive divider produces minus 1 volt. And then it stops because the inputs are at the same level, minus 1 volt. As you can see, this always amplifies the voltage by 3. Minus 1 volt turns into minus 3 volts, 2 volts turn into 6 volts, and so on. And the basic principle is that the voltage at the output always travels until it finds the equilibrium, until through the feedback both inputs end up at the same voltage. So this was the non-inverting amplifier, and there is also an inverting amplifier circuit, which again amplifies the input voltage but inverts its polarity. Let's, for example, give it 2 volts at the input, and let's say the output started at 0 volts, but now there is a positive voltage coming from this divider into this inverting input. The inverting input is higher than the non-inverting, so the voltage at the output will travel down until it reaches equilibrium, until it basically manages to get the voltage at this input to 0 volts, just like at the non-inverting input. It will travel down all the way to minus 4 volts, and now the resistive divider produces 0 volts and it reaches equilibrium. And this circuit amplifies the signal minus 2 times. It's very simple and most of you probably already know it, so now let's talk about some peculiarities of OpAmps. Of course, one thing is that the output voltage can only travel within the limits of the supply rails, minus some voltage drop of the internal switching transistors. So in reality it can't travel all the way to minus 15 or plus 15 volts. it might travel, let's say, from a plus 12 volts down to minus 12 volts. So for example, let's give this amplifier 10 volts at the input. Of course, based on the formula, the output voltage should be minus 20 volts now. Well, this is beyond the negative supply rail, so it's not possible for the output to go down to minus 20 volts. So it will basically go into saturation and the voltage will only travel down to minus 12. It can't travel down even further, so it will get stuck here. It will never reach minus 20 volts. If you give it a too strong signal, it will basically try to do something like this, but it's limited to the supply rails to plus and minus 12 volts. So in reality the output voltage will be clamped. And it will cause a distortion in the signal. And I'm using plus and minus 15 volts as an example, because this is the most common supply voltage for op-amps. Most op-amps are used at these voltages, and the output voltage can typically travel between plus and minus 12 or plus and minus 13 volts. And also most op-amps are using a symmetrical supply voltage, where the supply voltage has a positive supply rail and a negative supply rail, and they're the same magnitude but the opposite polarity. Of course, you can also use op-amps with a non-symmetrical supply voltage. It doesn't make that much difference from the perspective of the op-amp whether the supply voltage is symmetrical or not, because it doesn't have any supply pin connected to the 0 volt rail or the center point. So you can basically also see it as a positive 30 volts and 0 volts, for example. In both cases, there is 30 volts between the supply pins. But of course, with a non-symmetrical supply, the problem is that now the voltage can't travel down to 0. If the negative supply rail is called 0, then the output voltage can basically travel from, let's say, plus 3 volts to plus 27 volts, given the voltage drop of the internal transistors is 3 volts. And it can easily be the case because there are groups of several transistors in it, something like Darlington transistors, and their voltage drops are adding up. So remember, the output of an op-amp with a non-symmetrical supply can't travel all the way to 0 volts. And the range of the output voltage travel is called the output voltage swing. And if the datasheet says plus and minus 12 volts output voltage swing with a plus and minus 15 volt supply rail, then of course with a non-symmetrical 30 volt power supply, it will be from plus 3 to plus 27 volts. Everything in this example is just shifted 15 volts up. And to operate this example circuit with a non-symmetrical supply voltage, it will of course not work with 0 volts here. You'd have to, let's say, center it around 15 volts. And also the input voltage would have to be centered around 15 volts, let's say. Of course, now the schematic is a horrible mess. The voltages in red are the example of a symmetrical supply operation, and the voltages in green are the example of a non-symmetrical supply voltage operation. Now, for example, if you put 15 volts at the input, you have 15 volts at the output. If you put 16 volts here, you have 13 volts here. And of course, there is a lot of types of op-amps. Some of them are more or less meant for just a plus minus 15 volt supply voltage operation. Some of them are made for quite a wide range of supply voltages, let's say plus minus 2 volts to plus minus 20 volts, which with a non-symmetrical supply would be the same as 4 volts to 40 volts. And there are also op-amps optimized for just low voltages, let's say 3, 4, 5 volts. And they are often types optimized for a non-symmetrical supply voltage. And the symmetrical or higher supply voltage op-amps have typically the output voltage swing limited symmetrically, for example 3 volts shy of the supply rails, and the higher voltage ones typically also have a higher voltage drop on the output transistors. On the other hand, op-amps optimized for a low voltage or a non-symmetrical supply voltage operation might have a non-symmetrically limited output voltage swing. As an example, an op-amp running on non-symmetrical 5 volts, and the output voltage can actually swing quite close to the 0 volt rail, let's say 0.1 volts. But up to just 3.5 volts. The output circuitry is non-symmetrical and its voltage drop is much higher in the positive rail than it is in the negative rail. And of course, how far from the supply rails the output voltage can swing also depends on the load. The more load, the more the internal transistors will drop. The voltage at the output can swing farther when it's less loaded at the output. So remember, if the op-amp runs on 5 volts, you can't expect the output to be able to go all the way up to the 5 volts. There is always some internal voltage drop. And not only the output voltage swing is limited in op-amps, but also the range of input voltages. There is always some range of voltages you can have at the inputs. And op-amps, unlike comparators, are typically running with a feedback and not in a saturation. So the feedback basically keeps the voltages at the inputs the same. And that's why in OpAmps, the datasheets typically talk about the common mode input voltage range. The voltage of both inputs basically travels together, and it can travel in a certain range. And this is where a lot of beginners go wrong. Most OpAmps are using plus and minus 15 volt supply rails, and the voltage at the inputs can only travel between, let's say, plus and minus 12 volts. The voltage basically can't go all the way to the rails. It can't go here or here. The OpAmp won't work with the input voltage too close to the supply rails. Or at least for most types of OpAmps, the input voltages can't go to the rails. Of course, there are some types of OpAmps where the input voltage can go all the way to the rails, or even a bit beyond the rails. But only in some types, definitely not in all OpAmps. There are big differences between the types. You cannot just substitute one type of OpAmp using a different one without looking into the datasheet. OpAmps where the input voltage can go all the way to the rails are called rail-to-rail or full-swing OpAmps. And of course also in some OpAmps the range of input voltages is limited non-symmetrically. This is quite common for OpAmps optimized for a non-symmetrical supply voltage. The input voltage can go to the negative rail or even a little bit beyond, but it can't go too close to the positive rail. For example, for some at 5 volts, the limits are from minus 0.2 volts to plus 3 volts. So they can be used for small signals around 0, or for signals going between 0 and a certain voltage in the positive side. And there are even types limited non-symmetrically the other way, where the input voltage can go to the positive rail, but not to the negative one. For example, my battery analyzer is using an OpAmp running at 5 volts non-symmetrical, and it's sensing the voltage on the current sensing shunt in the negative rail, which is basically the 0 volt rail because it's not symmetrical, and the OpAmp has to be able to operate with 0 volts at the input. Now let's take a look at some examples of OpAmp datasheets. 741 is a very common old school OpAmp. Here are the absolute maximum ratings, but you actually want to look at these, the recommended operating conditions. The supply voltage is from plus minus 10 to plus minus 22 volts, but the nominal is plus minus 15 volts. This is the voltage most old school OpAmps are using. And as you can see, the minimum is plus minus 10, which with a non-symmetrical supply would be 20 volts. So this is really not for a low voltage operation. Somebody tried to use it in my battery analyzer at 5 volts, and of course it did not work. And here's the offset. Of course, ideally, the feedback tries to get the outputs to the same voltage exactly, but in reality nothing's perfect. The inputs are a bit offset by a certain voltage, typically 1 millivolt for this OpAmp. And of course, depending on the application, 1 millivolt can be negligible or also a huge problem. But you can add a potentiometer to an OpAmp to basically cancel this out. It can be adjusted using a potentiometer in this range. The potentiometer is connected to the offset null or offset trim pins, in this case pin 1 and 5. And of course only some OpAmps have these offset null pins, typically just the ones where there is one OpAmp in the package. You can of course get 2 or even 4 OpAmps in one package, but these typically don't have the offset null pins for the potentiometer. And of course ideally the inputs of an OpAmp draw no current, or basically source or sink no current, but in reality they have some current, which is very small, some nanoamps, and there is of course some offset between them. Here is the input voltage range, where you can see the inputs can go up to plus minus 12 volts or plus minus 13. Of course the datasheet says the typical and the minimum here. The typical value is how far the voltages at the inputs can typically go, and it still works. But of course for a reliable design you have to look at the minimum, the worst case. And the datasheet only guarantees it to work with input voltages between plus and minus 12 volts. And here is the output voltage swing. Again a typical value and the minimum, but of course your design should be made for the worst case. And of course the more the output is loaded, the less is the voltage swing at the output. When it's loaded using a 10 kilo ohm resistance, it swings plus minus 12 volts. When it's loaded using just a 2 kilo ohm resistance, which draws more current, it only swings plus minus 10 volts. Which is quite limited given the supply voltage is plus minus 15 volts. And of course these values are always specified for a certain supply voltage. When reading the datasheet, always look at the test conditions, especially the supply voltage, but also the loading resistance at the output for the output specifications. And of course the OpAmp has some gain. Ideally it would be infinite, but in reality it's some big number, 200 volts per millivolt, which is like 200,000 times gain. And of course the bandwidth of OpAmps is limited. They can basically work up to some frequencies, and it takes some time for the output voltage to travel to the equilibrium level. Here the rise time is 0.3 microseconds. The slew rate, how quickly the voltage is changing at the output, here is 0.5 volts per microsecond. It has of course some supply current. Of course the design has to be for the worst case. It typically draws 1.7 milliamps, but you have to expect it to draw up to 2.8 milliamps. If you don't need the OpAmp to be very fast, if you don't work with high frequencies, the most important things are probably the input voltage range and the output voltage swing. And this basically means the inputs have to stay away at least 3 volts from the supply rails. And this is also why this OpAmp can't work in my battery analyzer, besides the supply voltage range. Now the OpAmp I'm actually using, here it says the supply voltage, non-symmetrical 3 to 44 volts, which with a symmetrical supply would be the same as plus minus 1.5 volts to plus minus 22 volts. Here it says the bandwidth and a slew rate. This is basically how fast it is. The input offset, the output voltage swing. Of course the versions with 2 or 4 OpAmps in one package don't have the offset null pins. Here's even the schematic of it, nice. Again the input voltage offset, which can be compensated using the potentiometer. And here the specifications are for plus minus 15 volts. Well, sometimes the specification for a 5 volt non-symmetrical operation is completely separately. Here it's inside one table. For example, the output voltage swing is here for plus 5 volts non-symmetrical, the output high voltage, which is how high the voltage can go at the output, and for a 5 volt non-symmetrical operation, it can go up to typically 4.3 volts, but this is the typical value. Reliable design again has to be made for the minimum, which is the worst case, and the datasheet basically only guarantees the output can go up to 3.5 volts. And here the low output voltage for 5 volts non-symmetrical supply, it typically goes down to 0.05 volts, but of course you have to be ready for the worst case, 0.15 volts at the output as the lowest value it can go. Now let's take a look at the input common mode voltage range. The inputs can basically go from the negative supply rail all the way to the positive supply rail, minus 1.8 volts or minus 2.2 volts. And of course the range is more limited at the full temperature range in comparison to the 25 Celsius. But of course for a good design you want to use the worst case, which is this. And this basically means that with a 5 volt non-symmetrical supply voltage, the voltage at the inputs can go from 0 volts to 2.8 volts, 5 minus 2.2. And VEE is here the negative supply rail and VCC is the positive supply rail. And here again the slew rate, how quickly the voltage changes at the output at most, the gain bandwidth product. Of course in reality you can only use the OpAmp at a frequency several times lower than this. And somebody asked me whether he can use TL081 OpAmp in my battery analyzer. And take a look at this. It says the common mode input voltage range includes VCC plus, the positive supply rail, but not the negative supply rail. So unfortunately this one can't be used. This one would be actually suitable, for example, to sense the voltage drop on a current sensing resistor in the positive supply rail, but not in the negative one. But the voltage range would be suitable, 4.5 to 40 volts non-symmetrical. And the output voltage swing. In the positive rail, the output transistor basically drops up to 210 millivolts, and in the negative rail, 215 millivolts, when it's loaded using a 10 kilo ohm resistor. Of course it drops more, about 1 volt, when it's loaded using a lower resistance, 2 kilo ohms. This seems like a FET-based one. Of course some OpAmps are bipolar, some are FET-based, where the output voltage drop is basically lower typically, but it goes up steeply with the loading current. And of course the lower loading resistance loads it more. On the other hand, in a bipolar OpAmp, the output can drop a lot of voltage even with no load, and the voltage drop might not go steeply up with the current. And also the output voltage drop can be quite non-symmetrical, quite different between the high side and the low side voltage drop, especially for low voltage OpAmps or non-symmetrical supply voltage OpAmps. And also note that the input bias current and input offset current in FET-based OpAmps is orders of magnitude lower than in bipolar OpAmps. And an example how the offset null potentiometer can be connected to the OpAmp. But of course for different op-amps a different value of the potentiometer is recommended, and in this case the slider is connected to the negative supply rail, but some types of op-amps have the slider connected to the positive supply rail, and some have it connected to the center point of the supply voltage, which of course is inconvenient for a single supply operation because you have to make an artificial center point using a resistive divider. Here the offset nulling range is about plus minus 80 mV, which is super coarse. You can make the offset adjustment more fine by adding resistors in a series with the potentiometer. The total value is still roughly what the datasheet recommends, about 10 kΩ, but the adjustment range is about 1/3 in this example, or you can make it even more fine with these values. The total resistance is roughly what the datasheet recommends, but with these example values the adjustment range is just 1/20th. A different op-amp. For this type the datasheet recommends 25 kΩ for the offset null potentiometer, and it requires a resistive divider for a non-symmetrical supply. And I should also mention, some op-amps have a bias select pin. Here you can set 3 different modes of operation. For example, in the high bias it's the fastest, but also draws most power. In the low bias it's the slowest, but also draws the least power. And to select different bias modes, the bias pin is connected to different voltages. And of course the video is getting bloody long, but I have to mention one thing which can confuse the hell out of beginners. As an example, the 741 op-amp datasheet, the input common mode voltage range is just plus minus 12 volts. It's not rail to rail, but when you take a look at the absolute maximum ratings, it says input voltage plus minus 15 volts. And this can be very misleading, but this actually tells you what range of voltages is not going to damage the inputs. It does not mean that the inputs are going to work properly at these voltages. This might actually make it look like it's rail to rail, but it's not. So that's some basics about op-amps, and in the next video I can test these questionable op-amps from eBay, which based on the datasheet should work in my battery analyzer, but they don't. But anyway, I have some type that works in it. Now I also have the fuse holders for it, and after installing the fuse into it, I can test some sodium-ion batteries. So that's it, and if you like my videos, please consider supporting my channel on Patreon or using the thanks button accordingly to how much value you receive from my videos, or at least you can subscribe, and big thanks to all of you who already support me.